Love you madly. Love you madly. Good morning. Okay, we'll get started in just a moment. Good morning, everybody. Looks like we've got some people here. And I will go ahead and get started in just a moment. And cool. Huh. Interesting. Okay. Good morning. Good morning. Good morning. All right. So I think it is just about 8 o'clock. So if you are ready, I'm going to go ahead and get this party started. Let's see. Last class, we had just completed talking about planetary nebulae. And a planetary nebula. So what is a planetary nebula? A planetary nebula, what is it? They're kind of like shells of gas. Oops. Shells of gas. Happy birthday. Hope you do something special for yourself. Okay, so let's see. This is a little bit delayed from my, let's see, I can see this. All right, we're just a little bit behind here. I'm wondering if I'm behind is what happens. Okay, so I'm going to try to click the link again and see if, oh, it does show up. Perfect. Okay, so I couldn't see the writing. So shells of gas that are ejected by a red giant. And last time we saw that they're not always spherically symmetric. In fact, they're very interesting, and it turns out we don't know everything about how they're formed. There are some interesting details that we don't know. So let's see, I'm gonna point it back at me. Good morning, hello everybody. It's a beautiful day in the neighborhood. Well, okay, so it's kind of rainy out, but you know, we're here and we're going to do our best to engage in some interesting stuff. It turns out there is really some neat research going on right now related to topics that we're going to be covering in our class. There was a neat article on the most, actually I should show you guys. I should show you this really cool simulation of a planetary nebula, protoplanetary disk forming. Actually, you know what? Let's do that. Why not? Does it matter? Let's just do it. Hold on, let me just find it real quick. So yeah, let me switch back to here while I find this. Okay, so good morning, and then we'll put that little note up, planetary nebulas. So this was a new simulation that was just done. To show the magnetic field, brand new simulation. Let's see, it's in the news. Oh, here it is. Okay, I found it. That was fast. And there's a little video. Oh, cool. Okay, here we go. So let's see if I can watch it on YouTube. That's much better. We like YouTube. Okay, actually, I don't know if there's sound, so let me just try this. Okay, so I'm going to go ahead and show you this link. Actually, I'll put the link in later, and then you guys can watch this. This is a computer simulation. I don't know if there's sound, so I'm going to listen. Okay. Oh, there is. Okay, so that is a research simulation that was done to show a protoplanetary disk. And I don't know, did anybody see anything on there that was new to them? Because I sure did. I saw something that I was like, what? That's very interesting. Anybody? Anything new? Can we have animal farms on the moon colony? Definitely. We need animals, right? We're going to need some companion animals for sure, but maybe even farm animals, right? We can have chickens. We can have eggs on the moon. I want to have an omelet on the moon. All All right, so did anybody see anything interesting in that video that you hadn't seen before? I know that I found something incredibly interesting about that simulation. It said in agreement with astronomical observations. Anybody see that? Something really incredible that I did not know. And if you didn't see it, well, you missed it. And I'll post a link so you can go back and watch it again. But anyways, what I saw was the protoplanetary disk. I saw two things that were really cool. Sheds angular momentum, right? Remember conservation of angular momentum? Well, the only way to get rid of angular momentum is to get rid of mass, right? And in the process loses 90% of its original mass. That is what? I did not know that. Okay, that's news to me. So I'm not gonna put that on any test because I just found that out. But it's a really interesting idea. And it says that the magnetic field, you saw the magnetic field, sorry, the magnetic field is the process, right? Magnetic field, I'm gonna write this down. This is important stuff. Generated by the accretion disk creates a wind, right, that blows this material away. All right, so I'm paraphrasing, and it's not complete, but anyways, these are the concepts that I just saw that I thought were kind of new and interesting. So that is cool, right? In today's news, or that's actually yesterday, I saw that last night, and so as soon as I saw it, I'm like, what? We're just talking about protoplanetary disks. All right, so what are we doing today? We are completing chapter 13. Before we begin, I do want to make sure that you are aware of some cool stuff that's going on in the background. And some of you have been saying, please, extra credit, extra credit. And I heard your request, and I want to share with you. There is a new extra credit opportunity, and it's a really neat movie. I enjoy it so much. I find it inspirational, actually. And so if you take a look on your canvas, a couple of things. So we have, oh, you had a crash course in black holes today. Oh, black holes are awesome. I don't think we're going to cover them today, but next week we'll be talking about black holes. We may get to it. I don't know. Maybe we'll get to it. We'll see. We'll see what happens. Maybe we'll be ahead of the game. Your exam 3 is coming up. Okay. Actually, speaking of exam 3, don't forget that there's a study guide here. Now, actually, I may have made a little tiny mistake. I may have forgotten to upload the latest version. So let me just see if it's the latest version, and I will know right now. Oh, it's not the latest version. Okay, there's some minor little mistakes. I had to change last semester because of some new information. I'm gonna have to upload it. I'll tell you when we get there. It's just a tiny little mistake now, but it's because we got some new information last semester. Sorry about that. I forgot to change that. So here it is, the extra credit, the farthest. Actually, that's confusing. It's not called The Farthest Movie. It is a movie. So it's called The Farthest. Maybe I should, whatever. Anyways, you click on this link, and it takes you to a movie about the Voyager spacecraft. It's free. Okay, I'm not going to start it up. It's called The Farthest, and it's the Voyager spacecraft, and launched in 1977. This is an epic mission, right? It is really, truly an epic mission. And then there's just 4 questions. Give me a brief summary. This is 1 or 2 paragraphs, please. Don't write too long. It's mainly just for you to prove that you really watched the movie and you got something out of it. Tell me one thing that you found most interesting about the movie. What was the question that you had after watching the movie? And would you recommend this to other people? And why or why not? Yeah, I mean, what about it would you recommend? Or maybe you could say it's not really that great. It was kind of boring, or, I don't think you're going to say that, but, just let me know. I'd like to know, if it's worth recommending to other students or not. Okay, so that's an extra credit opportunity. How much extra credit? It is worth 5 points of extra credit. You don't have to go anywhere. You don't have to pay anything. You just have to spend a little time. It's about an hour and a half, I believe. Okay. So it's really a neat movie, though. I think you'll probably enjoy it. Okay. All right. So that's an extra credit opportunity. There is another extra credit opportunity coming up. And that is a guest speaker is going to be speaking, and he's going to do a kind of a Zoom thing that we've been doing, except we'll have a moderator who will take all of your questions on YouTube and be able to ask. You'll be able to ask your questions after the lecture. So we'll be telling you more about that. But anyways, that should be coming up pretty soon. Ooh, one more thing. Don't forget that we have our tutors. Please don't forget our tutors. Our tutors are there for you. And in fact, today we have tutors. Today is Thursday. So we have tutoring actually by Tori today. Okay, so not until 10:55. And you click on this link and you're going to go to Google Meet. Julian was a little unhappy because nobody came to visit her yesterday. She was worried that she was doing something wrong. And actually nobody went to go see her, I guess. Unless you can tell me that you had problems getting to her, if you click this link, it's supposed to take you to a room where she's working, okay? And there's no passwords or anything, so it should be okay. Yeah, here, if you're connecting, blah, 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 you're gonna click this link, I guess. But anyways, why would you want to go to the tutors? Well, guess what I just gave the tutors? 10 advanced questions, okay? So they have their 10 questions that are going to be on the exam on April 21st, and you can go ask them about those questions now. The PAL session, by the way, went on last night. Only one person showed up, but we will have another one on Friday with Liz, and I meant to put up the link and I forgot to do that. I will put that on my list of things to do, and I will have the Zoom session link available for you. Now we have to use a password, but we'll leave the password for you, okay? All right, so I'm back and I'm ready to begin the lecture. I'm gonna look and see if anybody has questions. Good morning, good morning. And I don't see any questions at this moment. So if you are ready, let's do one last thing. Let's take a look at the astronomy picture of the day. Okay, why not, right? Just because, for no other reason, just because. Beautiful. So remember that if you look around, you will find beauty everywhere you look. And part of it is looking at the world with an optimistic point of view, that no matter how hard the situation seems to be, there's a way for you to get through this, to be strong. And I know this is a difficult time. It's a difficult time for everyone. So I would encourage you to be patient and compassionate, and try your best to remember that everybody is feeling the stress and the strain. And so take a look at this beautiful composite picture. This is a picture taken, actually, if you look at the description, this person went to the desert, and this is a combination of time-lapse landscape panorama taken between 4:30 and 7 a.m. Across the New Mexico desert. And so you can see over on the right-hand side of the page, he still has the Milky Way, beautiful stars of the Milky Way. I can see this is the constellation of Sagittarius, right? This is the teapot, and the constellation of Scorpius. And if you were in the lab, I would tell you this really cool thing, that this is the shape of a teapot. I'll show you a little bit later, I guess. Actually, I will show you this. If you go over and up right here, this is the center of the Milky Way galaxy. And we know that something exciting is happening there. That's going to be our topic for for our final exam for after the exam 3. But I'll go ahead and tell you right now, there's a supermassive black hole. It's called Sagittarius A star. Okay, so I'll tell you probably several times. But anyways, that's a beautiful picture. So beauty is all around us. Beauty is inside of you. And so just remember that, give yourself a break, by the way. If you are feeling critical of yourself, make sure to step back and say, this is a difficult time. And you know what? I'm going to give myself a break and learn. If you've made a mistake, learn, move forward, have a growth mindset. Okay, so without further ado, we will begin to look at chapter 13, where we finished last time. And the lights went out, but you won't need to know that because Did you see the lights go out? That's funny. Okay, here we go, chapter 13. So we saw last time, these are protoplanetary disks, and the protoplanetary disks are not spherical, but they have interesting shapes. Now, I would say, first of all, that we don't know exactly why the shapes are there. I do see the two lobes, by the way, and as soon as you see two of anything, you should think magnetic field, because that's what it says to me. But there's other things like little pulses and interesting shapes, you know, that are clearly not spherical. What could be causing them? And so it's like a pulse of activity that happened. And one idea, it's not necessarily the only idea, but one idea I would like you to be aware of, because it will be on your next exam, is that a star, when it grows in size and becomes a red giant, will eat up the planets that are nearby. And during that process, those planets will stir the interior and cause waves of material to be ejected from the star. It will actually generate new waves of material. So it is not the only explanation, but it is an explanation. Okay. So here is another story that may be part of it as well. This is a binary star system with a red giant with a white dwarf. Okay, so we've already talked about this before, but these two stars were born together. And one of the ideas that you should be aware of is that this star has died already, and this star is still alive, right? It's in the red giant stage, or the asymptotic giant branch, which is a red giant. It's good enough. Let's call it red giant. Which one of the stars must have had a greater mass? Okay, so I would just think about that for a moment. You know, let's just take a moment to think about that. Which one of the stars must have had a greater mass? And of course, okay, so Anna asked the question, could the rotation of the star affect the spreading of the planetary nebula? Yes, in fact, we see rings of material being ejected by the what? Okay, we see rings of material being ejected by the star, and actually the planetary nebula can have rings, but the shape that we're really interested in is going to be the ones that are not the rings, right? The kind of more interesting shapes, right? So oblong shapes. That didn't make sense. So yes, that's true. But let me go back to my question. The question was, which one of these, the red giant or the white dwarf, was the more massive one? Does anybody know the answer to that question? I'm getting back on target. Okay, and the answer is it must have been the white dwarf, right? The white dwarf went through its life and died, and it died first. So it was more massive than the red giant. So we're in an interesting situation now. We have the red giant and the white dwarf next door, and the red giant is going to be expelling matter, right? And what's really interesting is that we have this term called the Roche lobe. Okay, the Roche lobe is this region between the two stars where the matter has to decide, should I go with you or with you, right? Should I stay or should I go? And once it gets past this point right here, this is the point of kind of equilibrium, that once it gets into this region, it's now in the domain of the white dwarf. And so it's going to be captured, right? So the white dwarf is feeding on the red giant, right? Because the red giant, now we're not looking at all of the material, we're just looking at the material that's in between. So a lot of the material gets out and escapes, but some of the material gets captured. And that material gets captured and goes into an accretion disk around the white dwarf. So remember that the accretion disk is going to be very hot. Okay, I don't know if you remember that already, but the accretion disk of this white dwarf is going to be really hot, and it's going to actually emit X-rays, it turns out. And because it's so hot, it's going to be highly ionized. So this will be a plasma that's circulating, which means it will generate magnetic field. And so you get jets coming out of it. Okay. Now, some of this material is going to land on the surface of the white dwarf. Does anybody remember what happens to the material that lands on the surface of the white dwarf? And some of you might remember the name. It's called a nova. So the material that lands on the surface of the white dwarf is going to fuse very, very quickly, and then it's going to nova. So here is an example of how this star ejecting its shell could end up being influenced by a neighboring companion, right? And could end up having jets of material that are shooting out. And so we don't see the companion necessarily. We just see, you know, the jets of material coming out. Okay, so blah, 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 blah. Yeah, don't worry too much about this slide. Okay, so so here, this is a question. What about that little white dwarf? Why is it that the white dwarf collapses but doesn't continue collapsing, right? So gravity is pulling that white dwarf together. And by the way, if everybody remembers, what is the composition of a white dwarf? This is a question that will be on your exam, right? And we talked about what happens with a white dwarf. A white dwarf is a star that doesn't have enough mass, right? So a white dwarf, right? A white dwarf will form from a smaller forms is the remnant, that's the word, remnant of a smaller mass star. So what was the original mass of the star? It turns out less than 8 solar masses. That's something that you should kind of know, and I'll tell you more about that later. Okay, so less than 8 solar masses. So if it has less than 8 solar masses, then it will be able to so it fused the hydrogen, it fused the helium, right? It used this as fuel, right? This was fuel, right? And then it made an ash of helium. And then it fused the helium and made carbon and oxygen, carbon and oxygen ash. Okay. But then it couldn't ever fuse these things, right? So what is a white dwarf made of? A white dwarf is made of carbon and oxygen, okay? So it's the carbon and oxygen that couldn't be fused. And it's mainly the core, right? The core of the dead star, right? The rest has been blown away. The rest is blown away to make these beautiful planetary nebulae, okay? So the question is, let's see, the question is, why doesn't, so what happened? The white dwarf collapsed because gravity collapsed it, but why doesn't the gravity keep going, right? What stops gravity? Actually, I don't know. So I'm just trying to motivate this question here. Why doesn't the inert core get crushed? Okay, so you need to learn a new concept, a new idea. And today we're gonna venture into territory that is a little bit strange. It's part of the quantum world. The concept that you're about to learn is a quantum mechanical concept. And it comes down to a principle that actually, I don't think this is part of it, but actually let's write it down. Okay, we'll write it down. What is the Heisenberg uncertainty principle? This is a very interesting idea. It says that there are 2 quantities for a quantum particle. And if you try to be very precise and for example, if you want to know the location of a particle, if you're very careful and you measure very precisely the location, something happens. If you know this really well, the location really well, it turns out that the velocity of the particle has to be unknown. There's a certain level of uncertainty in the position or the velocity. And so when you take something and you squish it down to a small size, in a way, you force the particles to be on that object, on the white dwarf, for example. But in the process of being on the white dwarf, it turns out, being confined, they have to have uncertainties in their velocities. They end up moving a lot faster. So you can't squish these particles down to an extremely, I mean, well, smaller than a certain size. Okay, so this is a very funny thing. It has to do with white dwarfs. And if you see right here in the middle of this planetary nebula, what is powering the light, right? What makes the light come out? What makes the gases glow? Why is it a nebula? And the gases were ejected by the dying star, right? That's true. But what makes them glow is this little tiny thing in the middle, the white dwarf, which is so hot, like 100,000 Kelvin at the surface, that it is shining with ultraviolet light. And that ultraviolet light is what's powering the planetary nebula. Now, after a while, so I have been reading a little bit more, and for years I've been saying it only lasts for about 500 years, but now I just read a very current article. I think they last a little bit longer than that. It turns out maybe closer to 10,000 years. Now, in astronomical terms, that's still a blink of an eye, right? It's just a tiny little amount of time, but just be aware that it's maybe more than 500 years. I might be wrong about that. And even Phil may be wrong about that. So anyways, don't worry too much about that. But so here's the term. Okay, so I'm going to go ahead and actually, I'm going to stop my share and I'm going to write down what, so here's the question. So what force stops gravity in a white dwarf? Okay, that's our question. You need to know the answer. And the answer is the electrons. There are a lot of electrons. In fact, every atom, and you notice I said atom, because when this thing collapses, you get basically a bunch of atoms. Every atom is surrounded by electrons. Now, it turns out there's a lot of extra electrons as well. And so the electrons are going to be zooming around inside of this white dwarf. So we said that if we confine them, the confined electrons, right, what it means is that they can't leave this volume of space. The more localized we try to force them to be, the stronger we push them into a center, the more they have to have an uncertainty in velocity. And it means that the more you try to hold on to them, the more they try to escape, right? They're going to have greater velocities. And so this term that you need to know is called the electron degeneracy pressure. Now, I normally don't mention this, but because it's a YouTube video and you can, just gloss over it or ignore it or rewind it and listen again if you want, I am going to tell you what this word degeneracy means, right? It turns out you don't need to know it, but it means they have the same energy. And that's pretty interesting. It turns out in quantum physics, when you have a bunch of degenerate particles with the same energy, when they occupy the same space, what do? They push against each other. This is not just the repulsive force, right? We know that electrons repel each other already, but it turns out it's another force. This degeneracy pressure is because electrons cannot exist in the same state. Electrons cannot exist in the same quantum state. It is not possible, okay? So there's another term that, again, I don't think you really need to know. It's called the Pauli exclusion principle. If you're interested in learning more about that, that's a really interesting topic. But this Pauli exclusion principle is the reason why atoms get bigger the more electrons you put in them, because the first couple of electrons can sit very close to the nucleus, But once you try to add a third one, it can't be closer to the nucleus anymore. It has to occupy a shell which is further away from the nucleus. So again, if you take chemistry, it's something that you do learn about. It says that when you have the nucleus here, the electrons have these places, orbitals, and you can only put so many electrons in before you fill that shell, and you have to jump up to a higher level and then jump up to a higher level. The more electrons you have, the larger the cloud. So I'll write that down for you. That's kind of interesting. More electrons equals a larger cloud of electrons. Okay, so that's interesting. But those electrons are going to reject each other, right? They're gonna say, not only do they repel each other because of the negative charges that they have, but because they have this degeneracy pressure as well. Okay, so it's a different kind of pressure. So you need to know, need to memorize. What stops gravity? And the answer is the electrons stop gravity. Okay, and it's known as electron degeneracy pressure. Okay, so electron degeneracy pressure is how white dwarfs exist, right? If you didn't have something to stop gravity, what would happen? Gravity would continue to crush it. And we will hear a story in a little while where that in fact happens. Okay, so this is an idea that you need to know. A white dwarf is a star-sized mass which actually has a size of about a planet when you compress it down, right? So it is, okay, half the mass of the sun. Well, it can go all the way up to more than the mass of the sun. We'll talk about that in a moment. So it's, about the amount of matter in a star compressed down to the size of a planet. So you're supposed to know that white dwarfs are the size of a planet. Okay, that's the only thing you're supposed to get from this slide. Okay, but it has a mass of a star, maybe half, but anyways. Temperature of about 100,000 Kelvin. Over time, I mentioned this last time, the white dwarf atmosphere will radiate the energy away. It will cool off, but in fact, there are no white dwarfs in existence that have cooled off and become black dwarfs. They don't exist yet, okay? There hasn't been enough time for them to cool off. So that's true, this is true, and yet it's not true, right? It's kind of like, yeah, sure, okay. But we're talking about billions, maybe even a trillion years for them to become black dwarfs. Okay, so this is the full path of a white dwarf. And by the way, this is showing you the future, right? We haven't seen this. This is not, we haven't seen a white dwarf cool off yet. It's never been seen. I promise you, it has never been seen. It hasn't happened yet. Okay. So remember, you're supposed to know what happens when you go horizontally and when you go vertically, what's going on, right? Horizontally, you're cooling off, right? You're cooling off, but your luminosity is not changing. So how do you do that? Well, you have to expand. You have to be bigger, because each square meter is producing less light as you cool off. You have to have more square meters. If you go vertical, your temperature is not changing much, right? But you're producing a lot more light. Again, you have to get bigger. Okay, so those are the two kinds of changes that you're supposed to know something about. All right, now, it turns out that a very brilliant physicist, astrophysicist by the name of Subramaniam Chandrasekhar was able to do a theoretical calculation. Theoretical, this is all theoretical. And we still have a little bit of, we don't quite know for sure exactly how this works. There's still some little mysteries here. But it turns out that we have seen something very interesting. If you look at this chart, right, how does it work? The greater the mass, the smaller the size of the white dwarf. And there is a limit, right? There is a limit. And how does this work? Well, it turns out the electron degeneracy pressure has a certain strength. And this fellow, we want to be really impressed. This is the name, Subramaniam Chandrasekhar. You should write down the Chandrasekhar limit. You need to memorize this number. The Chandrasekhar limit is the maximum mass of white dwarf. Okay, so the maximum mass of a white dwarf, the Chandrasekhar limit, this is really important, right? We're about to describe some really awesome physics, but we need to understand why that happened, right? So the mass of a white dwarf must be less than 1.4 solar masses. 1.44 it turns out, but don't worry about that. 1.4 solar masses. So he calculated the strength of a white dwarf. Sorry, not the strength of white dwarf. The strength of the electron degeneracy pressure. He calculated the electron degeneracy pressure and was able to see that it had a maximum mass of, that a white dwarf should have a maximum mass of 1.4 solar masses. Why is it a maximum mass? Can anybody explain why that should be a maximum mass? What happens when you have more mass, right? What happens when you have more mass? And I don't see people answering my question. So I'm just going to go ahead and just ask it rhetorically. If you have more mass, if you go above this limit, more mass equals stronger gravity, right? Gravity. And so what does it mean, right? That was my lights going out. Sorry about that. More mass equals stronger gravity. If you have too much mass, what happens? The electron degeneracy pressure is not strong enough. Loses, okay? So gravity wins. And by the way, gravity always wins. Okay, so gravity always wins. That's the story. Gravity always wins. So more mass is stronger gravity. Too much mass and the electron degeneracy pressure loses. So what happens then? If you have more than 1.4 solar masses, then you can't be a white dwarf. So then what? What happens? The electrons, which have been strong enough to hold up this white dwarf, are not strong enough. Where do they go? Right? Where do the electrons go? I'm going to ask that question just so let you. Where do the electrons go? Okay, where do they go now? They haven't been able to. If you get too much mass, the electron degeneracy pressure loses to gravity, right? So what does gravity do? Squishes it together. Where do the electrons go? And the answer is into the nucleus. What? This is crazy. Oh my gosh. That's where they go. They're not supposed to go there. They never go there, but they do if you get too much mass. So now we want to consider, what does that mean? What would happen to an electron, regular ordinary electron that got squished into the nucleus? Well, here is the seed I planted a long time ago. Maybe you guys remember. In fact, neutrons are unstable when you take them out of the nucleus. Remember what they decay into? I don't know if you remember. But it turns out that when the electrons are forced into the nucleus, they will find some positive protons. And something miraculous happens. What is the miracle? What is it that happens? Those two can combine and form a neutral neutron. This is amazing, right? The electrons, when they get forced into the nucleus, will combine with protons and be neutrons, right? Which is, wow, is that crazy? So that is amazing. Okay, Subramaniam Chandrasekhar was the one person who figured out the strength of the electron degeneracy pressure and showed that if a failed star, if a white dwarf was greater than 1.4 solar masses, that it couldn't exist anymore, right? The electron degeneracy pressure would not be strong enough. So what happens, right? What do you get? So here is, okay, so what kind of pressure supports a white dwarf against the force of gravity? This is one of your questions, of course, on the quiz that you're going to be taking afterwards, and participation quiz. And the answer is B, the electron degeneracy pressure, of course, okay? So you're going to see that this is kind of a cool story. We'll talk more about this later. Okay, so here is more massive stars. Okay, we mentioned this before, but in fact, the triple alpha process is 3 alpha particles. Remember, helium nucleus is an alpha particle, and they form carbon, right? Here's how you form the carbon. Okay, so this because, okay. So when you have a very massive star, and by the way, this means greater than 8 solar masses, then you'll see something like this. So this is the onion skin kind of model. And it says that these are not red giants, by the way. These are called red supergiants, but it's a similar kind of story. You run out of the fuel in the core, right? Originally, the fuel is hydrogen. The hydrogen has been turning into helium. You run out of hydrogen and the core begins to collapse, right? The helium core begins to collapse. At some point, because you have enough mass, then that helium becomes a fuel. Then you start burning the helium. The helium turns into carbon, and the carbon ash will accumulate. Eventually, you run out of helium. And then what? Well, then the core begins to collapse again. And it turns out if the star is large enough mass, greater than 8 solar masses, the carbon will begin to fuse and it will form, and you can see there's a sequence of elements. You don't need to know the whole sequence, just the last element. This is important. Eventually, if you look at the core of any of these large mass stars, you will find iron accumulating in the star. And so this is a pretty big deal, right? This is a pretty big deal because something is happening, right? So you can get actually simultaneous burning of all of these fuels in shells, right? As this one produces helium, it can then burn in a shell. This one produces carbon, it can burn in a shell, and so on and so on and so on. Okay. Oh, actually, sorry, this is non-burning. So hydrogen, helium, carbon, etc. So a star goes all the way to iron and then can't go any further because something important, right? So this is actually a big deal. You guys probably already know this, but how does the star sustain itself against gravity, right? Remember that the star produces radiation pressure through the process of nuclear fusion. So stars are living, right? So stars use fusion to create radiation pressure, right? And the way it works is you do fusion of your fuel, whatever it happens to be. You get an ash as your product, plus you get energy. Okay, and everything's fine, right? Everything's great for a while, right? It could be hydrogen making helium, helium making carbon or oxygen, carbon making neon, et cetera, et cetera, et cetera. But then we get to iron. Okay, so what's the problem? If you remember, iron was special. If you remember the symbol, it was Fe, and in particular Fe56. This is the most, I'm going to use this word, efficient nucleus. What does it mean? It has the highest binding energy per nucleon. You can't do better than that. So what does it mean? In every other fusion, the product that you made had less mass than the material you put in. The extra mass released energy, E equals mc squared, right? This is E equals mc squared. But when you get to iron, if you try to fuse iron, which is already the highest binding energy per nucleon, what you make is less efficient. What does that mean? The ash has more mass than the fuel. So fusing iron requires energy. It doesn't release energy. It takes up energy. What happens when you take energy away from the core? The core cools, not heat. That's a bad day. Okay, so that's a bad day. Okay, so a star cannot fuse iron and survive. And in fact, what happens on the day that a star begins to fuse iron? I shouldn't say a day, sorry. What happens the fraction of a second after a star begins to fuse iron is it dies in a very explosive and beautiful thing called a supernova. Okay, so it turns out it will fuse all the way to iron, and then the moment, literally a fraction of a second after it begins to fuse iron, it will explode. It will die. Tremendous explosion. So we mentioned already this is something that can happen when a proton meets an electron. You can get a neutron, and also a neutrino is escaped. I'm not going to tell you exactly why, but some of you might be interested to know where the heck did the neutrino come from. But the neutrino actually was, and neutrino and antineutrino were being created. The antineutrino was needed to combine with the proton and the electron to form the neutron, and the neutrino escaped. Okay, so here is this is known as a type 2 supernova, and this is a computer simulation. Now, actually, I think I want to show you this. This is actually a really neat thing just to understand how crazy this is. Type 2 supernova simulation. Okay, let's see if we can find that. This is a very quick one, 8 seconds. Okay. This is 2019. Yeah, this is the latest one. So hold on, let me just get this. It's very quick, just so you understand. Okay, so this is from the Royal Astronomical Observatory, Royal Astronomical, I'm not sure who. Hold on, I'll tell you in a second. This is a supernova simulation, and you'll see the time here. This is negative 0.114715 seconds, and I don't know how to press start. Oh, there we go. There we go. So this is the collapse, because this, oh, well, that was very fast. Let's try it again. The collapse and the shock wave, and you can see it's like fraction of a second, and it's incredibly complicated. Actually, you know what? Let's find another one. Let's see, NASA supernova. No, that's not what I want. Actually, hold on. Simulation, right? Actually, I have this. Oh, here we. Oh, this one. This is it. Oh, that's too long. Okay. Oh, I don't want that. Oh, that's awesome, by the way. Oh man. Okay. This one. No, that's not what I want. That is awesome, by the way. Oh man. Okay, I'm not finding the one that I want. Oh, core collapse. 2 minutes. Should we watch that? 2 minutes. We have 2 minutes to spend. Pretty awesome. Let's see.
How do massive stars 10 times the mass of our sun
Core collapse.
Spectacular stellar explosions supernova take 2 deep points in the universe, without which life as we know it would not exist? Therefore, understanding how they occur is tantamount to understanding how we came to be in the universe. Consequently, one of the most important unsolved problems in astrophysics. Core collapse supernovae are complex, turbulent, three-dimensional events that will require multi-physics, multi-scale, three-dimensional simulation. These events probe extremes of nature that, relative to our everyday world, are simply unfathomable. Take, for example, the dense matter in the neutron star produced by the supernova, one of the supernova's remnants. 1 cubic centimeter, the size of a single sugar cube, would weigh as much as the entire human race. And the challenges don't stop there. Three-dimensional core collapse supernova simulations will produce data at the staggering rate of hundreds of terabytes per simulation. For scientific discovery, these data will have to be analyzed and visualized by scientists.
Okay, so it's a little bit too complicated, but let's see. So let's talk. Okay, so we have a star that has gotten all the way to iron, and the idea is that every element before iron, when you fuse it, the product that you make has less mass than the reactants or the stuff that you put in. And the leftover mass is turning into energy, E equals mc squared. But iron, when you fuse it, makes something which is more massive. So it actually has to suck energy out of the core. So it's just a fraction of a second after it begins to fuse the iron that the star collapses. So the core is actually the only thing that's going to stay behind, right? The iron core is going to stay behind. All the other shells of material are going to try to collapse behind it, but they're not actually going to stay. They're going to fuse very rapidly and then explode away from this little core. They bounce off of it in a way. And this is called a type 2 supernova. Okay, so let's write that down so that you have that in your notes, right? So this is a type 2 supernova. And it's a very exciting event. So it is a more massive star. What is the mass of a type 2 supernova? And it turns out it's greater. It's the starting mass, right? The starting mass when you at the very beginning was greater than 8 solar masses. Remember, less than 8, you become a white dwarf, but greater than 8, you're going to go all the way to iron. Okay, so anything greater than 8 is going to go all the way to iron. So what's left over is this iron core remains, right? Only a tiny little bit of the iron actually fused. So what happens to that core? And the answer is, well, it depends, right? How much mass does it have? First of all, it turns out that almost in this story that I'm telling you, the remaining mass is usually, it's usually pretty small. Actually, it's usually pretty small. In fact, it might be, you know, a half a solar mass or something like that. But the strange thing is, I know I messed up a little bit. I didn't explain how this works. What happens in this scenario, though, is no, actually, that can't be right. I'm wrong. Sorry, sorry, I'm totally wrong. The leftover mass is greater than, so the iron core is greater than 1.4 solar masses. Okay, that's why the story I'm about to tell you has to happen. So if you remember, 1.4 solar masses is the smallest, is the largest mass white dwarf you can have. What happens when you go above this? The Chandrasekhar limit, right? So the electrons merge with protons, right? In the core. And what do they become? Neutrons. So we're going to get a big, giant ball of neutrons. A big ball of neutrons. What do we get? We get a big ball of neutrons. Okay, what's the name, the scientific name for a big ball of neutrons? A neutron star. Okay, now these are incredibly dense objects. Actually, if you heard that guy's video, I don't think you could hear it very well, but he mentioned something that is kind of amazing, that 1 cubic centimeter one die, right? It's like one die, 1 centimeter cubed of neutron star material would weigh more than all the human beings on Earth combined. Anyways, something crazy like that. 1 cubic centimeter of neutron star material is greater than all humans on Earth in mass combined, right? That's kind of crazy how dense this is. But it's actually even crazier than that. So let's go back to our slide set, and I will show you the last part. So this is showing you this is a very complex calculation done by a supercomputer, and it's very confusing because we don't quite understand why sometimes it's kind of symmetric and other times it's not. And the models show that you can actually get these very asymmetric explosions for type 2 supernova. But anyways, okay. So this is kind of a famous thing. Actually, this is not the famous one. I'll tell you another famous one in a second. But type 2 supernovas are so bright they can be seen, right? We can see them in different galaxies. And they can last for a few months and shine with the energy of 1 billion suns. They're really powerful events. In fact, they're just incredibly powerful events. There was a really famous one that you should know about. Let's see, do I have time to tell you about that? Yeah, let me tell you about that. A very famous one that happened a while back, and actually it's the first supernova that we actually understood was an exploding star. It's pretty neat. But this bubble that you see is an example of a supernova remnant. And so what's happening is the shock wave from the supernova is extending in every direction. And what happens when it finds some interstellar medium, right? When it finds some interstellar medium, it's going to generate a whole new set of stars there, right? And so it makes a bubble, a giant bubble that we can see. So actually, let me just do what I would do in the classroom, is tell you a little story time class. And I would show you an interesting picture. This is a very famous nebula called the Crab Nebula. Okay, so I am going to go ahead and share the picture with you. 1 second. And let's see if this works. Okay, so I'm looking on Google, and I found a picture of the Crab Nebula. Please write down the Crab Nebula, and you'll notice that it has a catalog designation M1, which means Messier object number 1. It's Messier object number 1. It's a really cool story, and the book does a pretty good job of explaining what's so interesting about it. It's 6,500 light years away, plus or minus. Okay, don't worry about that. But the cool thing was that when we started looking at this, it was neat, right? It was, first of all, this beautiful glowy patch. They thought it looked like a crab, right? You can look at these pictures. They're kind of neat. But the really awesome part of it that you want to know is that they saw that it was growing, right? The Crab Nebula was discovered, and then they kept watching it, and then they realized that it was getting bigger. And so it was the first time that anyone had ever seen anything like this, right? A glowy thing that seemed to be getting bigger. So what do the scientists do? They say, well, let's figure out how fast it's expanding. And from that, let's figure out when it must have started, right? Let's work backwards, rewind the clock, and find out when the whole cloud was back at a single point. And they narrowed it down to a pretty small time frame in the year 1000. I mean, in the millennia 1000. And they actually looked up, and Chinese astronomers had recorded I wonder if we can find the picture. This is so cool. Let's see. This is really, no, this is not it. I would love to see that. But anyways, Chinese astronomers recorded the guest star of 1054. Let me see if I can find that. Guest star The guest star. Okay. Anyways, the guest star of the year 1054 was first was actually talked about by Chinese astrologers, astronomers, and I would love to see the original picture, but I don't know. I've seen some ideas of it, but or some pictures, but I don't know where it is. Anyways, they noticed the star, and supposedly the star was visible for 21 days during the day, and then for about 2 years at night. And basically, that gave them the idea that it was an exploded star, right? So the guest star of 1054, it was a star that just appeared, and Chinese astronomers noted it, and it was in the constellation of Taurus, the bull, and was visible during the daytime for about 3 weeks. Now, this is something none of us have ever seen. I think I've already told you this story now that I think about it. But anyways, just tell you again. And what was it? It was an exploding star, a type 2 supernova. Now, I want to ask this question now just to get it in your brain. Do we know the mass of the star that exploded in a type 2 supernova? Do we know exactly what its mass is? Nope, we don't know. We just know that it's above 8 solar masses when it started, right? That's all we know. We know that it went all the way to iron. If you have more than 8 solar masses, you go all the way. But that could be a really massive star or one that's just a little more than 8. It doesn't matter, right? So 8 or above is going to be enough to get all the way to iron. Okay, so back to our slideshow. And we mentioned, so the Crab Nebula is kind of an example of this. And the Crab Nebula is a great story to tell. Okay, it has the guest star of 1054. So there is another kind of nova that you need to know about. This is actually a nova is a non-terminal, non-deadly, right? Explosive nuclear fusion occurring on the surface of a white dwarf after it has accreted matter from a companion star. Okay, so novas are short-lived events. They're little tiny flashes that occur every time a white dwarf feeds on a red giant companion. And so this is that story that we told, right? It's a symbiotic, if you remember that word, symbiotic relationship, a symbiotic binary. And the red giant is giving a little bit of matter to the white dwarf. The matter falls onto the surface of the white dwarf. And what happens? It fuses instantly, right? This is probably mostly hydrogen, and therefore it's easily fusible because the temperature of the white dwarf is 100. Actually, that's not making sense. Well, okay, whatever. Yeah, I guess there's more to it than that. Okay, 100,000 Kelvin is not enough. I'm questioning. Well, we know there's a flash, so something happens. It does fuse. And forget about my confusion because you shouldn't worry about that. But anyways, the fusion occurs, and what happens to the products? Well, they are stuck there. They are stuck. And so every time the white dwarf feeds, every time there's a nova, there's a mass transfer. There's the white dwarf gets a little bit more massive, and that's fine, right? No problem. Except we might remember there is a limit. Don't forget, there's the Chandrasekhar limit. So I want you to imagine a situation, this doesn't happen all the time, but it happens enough that we should know about, where a red giant has a white dwarf companion, right? And that white dwarf has a mass of 1.38 solar masses. And you're like, well, that's no problem, no problem. And then, you know, there's the lobe here. So we've got this region of gravitational field. Right? If it crosses over, it belongs to the white dwarf. And, you know, then now it's 1.39. And the white dwarf is like, no problem, no problem. That's good. So every time it feeds, it gets a little bit more massive. It takes a while, right? And these happen time after time after time. They don't happen in a regular way, but they happen over and over and over again. As long as this one can live, it can give mass to the white dwarf. And then this one gets to 1.395 solar masses, and everything is fine. And maybe 1.399 solar, and everything is fine. But then one day, right? That little tiny extra little bit of mass takes it over the limit, right? On this day, it gets to 1.4 solar masses. Oops. 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 That's too much, right? What happens to the electron degeneracy pressure? Is it great enough to stop gravity? And the answer is nope. So what happens to all of that carbon and oxygen? It begins collapsing and heating and collapsing and heating and almost instantly fuses. So we call it a runaway nuclear fusion. All of that carbon and oxygen fuses, right? How much? Exactly 1.4 solar masses every single time. And we have a name for this. This is called a type 1A supernova. So these are two different kinds of supernova events that you have to be aware of. This is a white dwarf, which on the day that it gets just a little bit too much mass, becomes a type 1A supernova, okay? So this is, a pretty big deal. So this is a terminal event, right? So you can't keep going at that point. You are no longer the white dwarf, you have exploded. By the way, you probably take your red giant companion with you in the explosion, rip that star apart. Kind of exciting event, right? Anyways, okay. So at that point, blah, 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 blah. Okay, here we go. So it went above the Chandrasekhar limit, and then it ignites the carbon and oxygen in one quick moment called a type 1A supernova. These are really exciting, but the cool thing is that they are always the same mass, right? They're always the same mass. So one of the neat things that we know in astronomy is that we actually can compute, we can model, we can compute the absolute magnitude. So if you know the absolute magnitude and you see one of these events happen out there in the universe and you measure the apparent magnitude, then what can you calculate? If you know the absolute magnitude, the luminosity and the absolute magnitude, and you measure the apparent magnitude, you can figure out the distance. So type 1A supernovas are incredibly wonderful standard candles, okay? Standard candles. So the type 1A supernova is an explosive detonation. The nova was just a little tiny joke, right? The supernova is incredibly powerful, okay? So if we watch supernovas happening, this is something that scientists are doing. They watch the light curve from the supernova, and the peak of this light curve can be used to calculate the distance. So this is a pretty neat thing. So they are called standard candles because we know exactly how much mass. We know they are always the same amount of mass. We know their intensity of the light. Okay. So what about the type 2 supernova? Well, the type 2 supernova leaves behind a very tiny core of iron. And that iron core is actually going to, the electrons can't exist as electrons. They're going to merge with the protons, and they're going to form this tiny little ball of matter called a neutron star. So I'm going to pause for a moment just to actually talk about something else. The neutron star, right? Remember, the neutron star is this idea that the electrons combine with the protons to make a big ball of neutrons. So what you have is this incredibly tightly packed thing where all the neutrons are packed together, right? A whole bunch of neutrons. The protons are pretty much gone. There may actually be, all right, so I'm gonna just try to give you a simple picture. So we have a big ball of neutrons. It looks just like a giant nucleus. except there's no protons, right? It's just a giant ball of neutrons. And so this matter stops collapsing, right? So what does that mean? Well, actually, it means gravity got stopped again. What stopped gravity, right? What stopped gravity from collapsing it any further? And the answer is the strength of the neutrons themselves stopped gravity. And so the neutrons is the answer, right? The neutrons. But we actually have a special name for this, right? And again, it's not just the neutrons the way that we think about them being pushed up against each other. It turns out that neutrons, when you squish them together, don't want to be in exactly the same state. And so we have a name for this. It's called neutron degeneracy pressure, right? That's the name that we give this. Now, this is the technical term, neutron degeneracy pressure, which is it bigger, smaller, or equal to the force of gravity? And the answer is it is equal, okay? But similar to the electron degeneracy, there is a maximum neutron degeneracy pressure. And we are having a lot of trouble figuring out what it is. I wish I could tell you exactly. There is a maximum, and we just know that it exists, right? There's some point where you have too much pressure and the neutrons can't even stop gravity. Okay, so we'll get back to that in just a minute. So what I want to share with you is something amazing, right? What if the entire Earth, what if the Earth was compressed to this density? Right, just to understand, right? The entire Earth. How big is the Earth? Right? If I were in the class, I would ask you to remind yourself how big it is. How far? How big is it? 4,000 miles, 8,000 miles across, 12,800 kilometers across, right? How big would it be if it got squished down to this nuclear density, right? How big would the ball be? And you're not going to believe it. You're not going to believe it. I don't know what to tell you. It's just so amazing, but I got to tell you, okay? It is the size of a bowling ball. So you could literally hold the entire Earth in your hands, right? And your hands would be ripped apart by the gravitational fields, but it's almost incomprehensible. But the density of neutron stars is so great that the Earth would fit into the size of a bowling ball, which is like, I don't know, 30 centimeters. 30 centimeters across. 30 centimeters. The entire Earth. So make sure you understand matter is mostly empty space. If you didn't believe me before, now maybe you understand what I mean by that. When you make a density, a neutron star, sorry, you make something that has almost no empty space. And so that is an extremely strange, bizarre creature, okay? So, all right, so we've talked about this, and now you can see, right, the neutron star is a tiny little point. Actually, it's the size, you're supposed to know, the size of a city, 10 miles across, right? A star-sized mass. Now, I disagree with the author, and I actually have proof now that he's wrong. He put 1.4 and 2.1. I'm going to change that. I'm going to change that for you. The number is changing. I don't know the exact number, but I'm going to go like this. I said that if the mass of the remnant, let me put remnant mass. Let me put remnant mass is, if it's less than 1.4 solar masses, what do you get? You get a white dwarf. Okay, that's a white dwarf. And by the way, what holds the white dwarf up? Electron degeneracy I can't read that, but degeneracy pressure. Hold it up, right? If you have greater than 1.4, and I'm going to put up to about 2.7. This number is not precise. I don't know. I actually don't know this number is 2.7. What I know is that it's bigger than 2.4, but I'm not sure if it's 2.7 or not. But I know 2.7 is too big, right? Then you get a neutron star. Right, which again is held up by neutron degeneracy. I'm just going to put a dot there, pressure. But I now have a story which came out last year. And if it's greater than 2.7 solar masses, this is different from the study guide. I used to have 3 here, but last year something happened and I had to change this to 2.7. It used to be 3. It's just a small change, but it's important that you know this. What happens if you have 2.7 solar, more than 2.7 solar masses? The neutron degeneracy pressure is not strong enough to stop gravity. So what stops gravity? And the answer is nothing. Gravity wins. So what do you get when the ultimate force of gravity, when gravity is too strong to stop you? Then what you get is a black hole. There is no force. Gravity wins. Is too strong. There's nothing to stop gravity. Then you get a black hole. Okay, so that will be our topic for next week. Let me see. I do have to tell you a last little story, just a quick little story, but an important little story. Blah 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 blah. Okay. Skip that for a second. Okay, this is actually the story, right? This is or part of the story. So if you take a star, which is already rotating, and even if you're only using the core of it, when you squish it down, of course, what happens? It has to rotate faster. Conservation of angular momentum. Very good. And so we have seen something really interesting that neutron stars rotate. They have incredibly powerful magnetic fields, probably because they have some material trapped, but I don't know that. I don't know. Actually, I don't really know. I don't really know. I just know they have powerful magnetic fields. You should write that down. Neutron stars have powerful magnetic fields. And as a result, they make these jets of material. Now, it turns out sometimes the jet is pointed at the Earth, right? And if it is, then we will see it. Actually, you know what? I just realized, even though I only have a couple minutes, I just want to show you. This is the lighthouse model for a pulsar. And I want to see an image. Maybe actually, can I do an animation? That'd be cool. Let's see if I can even find a video. Let's see. All right. Oh, that's cool. Okay. All right. So I have a little video here. Let's tab over, and I'll share that with you. This is a neutron star with a jet, and the idea is that if you watch the jet, it's moving in different directions. This is called the lighthouse model, and we can see that jet if the jet happens to be pointed at the Earth, right? And if it does, by the way, it'll do it probably time after time after time. And so it will repeat itself. And the name for these is a pulsar, right? These are called pulsars. A pulsar is a rapidly rotating neutron star. Write that down, a rapidly rotating neutron star. Now, some of them are rotating almost 1,000 times per second, and that means that it only takes a millisecond for one rotation, and they're called millisecond pulsars. So I think I'm gonna just do one last little thing with you. I want to tell you about Jocelyn. Jocelyn Bell was a graduate student getting her PhD in radio astronomy. And she and her advisor, Anthony Hewish, her advisor actually gave her the money to build one of the first radio arrays. And when she started using it, by the way, there's a whole story here. She kind of got cheated out of a Nobel Prize because she did most of the work, but her advisor got the Nobel Prize. Let's not worry about that. But what she saw was something really crazy. She saw pulses of energy in the radio frequency. And it was a little bit confusing. She thought, actually, it was really fun because just recently, the first satellites had been launched into space. She thought that this was a man-made signal. There's no way, it was so regular. There's no way this could be a space-based signal. And then they found 2 more signals, and they didn't know what they were, but you want to write down, this is my last little note for today, the Jocelyn Bell, with her radio telescope, saw these signals, and she called them LGMs, right? LGMs. What does LGM stand for? Some of you know this already. Little green men. They thought they were aliens. Okay, so I didn't quite finish chapter 13. We're almost done, but I will go ahead and finish that on Tuesday for you. And please look for your participation quiz. It's based on the material that we covered today, chapter 13. And again, we just have a couple more slides. We're basically done with chapter 13, which means next week we can do chapter 14, which is awesome. And of course, we're going to have to cover black holes. So thank you very much for being here. And if you have any questions, I'm happy to answer those questions now. But at this point, the official lecture is over. Yes, I see someone type something. So thank you. Thank you, and have a good day. Thank you, and have a great day. And I will see you guys on Tuesday. If you have any questions, go ahead and ask them. Otherwise, happy birthday, fabulous cat on a unicorn. Have a wonderful birthday day. Hope that you have a fun time. Thank you. Thank you, everybody. All right, we'll see you later.